Alright, let's get the show on the road. Good afternoon, I'm Peter van Gelderen. Today I'll talk a little bit about the theory of T1 relaxation and magnetization transfer as part of the fMRI summer course. Short outline, we'll talk about two relaxation mechanisms relevant for magnetic resonance imaging. Short overview how you can measure T1, and then go on to magnetization transfer, since that is closely related to T1, how you measure that, and lastly, if you have time for it, a little bit about the combination of both of them. So to understand T1, we start at the very beginning. What happens if you put nuclear spins in magnetic field? As you might know already, following this course, or maybe not. You can, with some quantum mechanics, find that spins that are parallel to the field have a slightly lower energy level than spins that are opposing the field. And from quantum mechanics we know spin and a half particles, as hydrogen protons have only these two states. And now since the energy level is slightly different between the parallel and anti-parallel spins, if you have a large number of molecules, put them in a magnetic field, more of them will align parallel to the field than anti-parallel, and that means your sample is getting magnetized. So the amplitude of this magnetization is pretty small, since the energy difference is tiny compared to the thermal energy at room temperature. So that means even at a 1 Tesla magnet, it seems fairly strong compared to the normal magnetic fields you encounter in daily life. You end up only with 1 out of a million energy difference, or population difference. It also explains that stronger magnetic fields help to get you a better signal, since of course the energy difference is proportional to the magnetic field. So with a strong magnetic field you have a bigger magnetization, stronger signals. So now we know nuclear spins polarized in a magnetic field. The question is, how fast does this happen? Because the change in polarization, going from random orientation to the change in population difference, requires an energy transfer from the spin system to something else, and the something else is typically the thermal vibration of the molecules in the sample, and in our case typically the water. So there needs to be a process that can transfer the energy from the magnetic polarization into the vibrations of the water, and that limits how quickly this process can happen. So we can derive the general time course of this process with a mix of some quantum mechanics and classical approaches. If you assume that every spin has a certain probability to make the transition either from the down state to the up state, or the reverse, where P minus is slightly bigger than P plus because of the energy difference. So the spins have a small preference, of course, to be in the lowest energy level. And then we can take two more variables, n minus and n plus, to indicate the number of spins in each level. So we can calculate the magnetization of the sample as the difference between these numbers. And the change in magnetization is then the number of spins in each energy level times the probability that they cross over to the other level. And now, so for equilibrium, the change in magnetization is 0. So in equilibrium nothing happens anymore. So from that we can derive that the ratio of the population numbers in the two energy levels is proportional to the probability of this transition. Now if you have a disturbance in the system, So the magnetization is not equal to this equilibrium value, but it has some kind of, let's see if I can get a cursor. Yeah, there we go. So if you have some kind of a difference with respect to the equilibrium, now we can start to calculate how this difference evolves over time. You can derive that the change in magnetization is proportional to the distance from this equilibrium level times the combined probability, transitional probability. So in other words, that means the change in the magnetization is some kind of a constant times the difference of the magnetization with respect to this equilibrium. And this constant is of course the T1 relaxation. So this equation of course solves into exponential decay, and then the decay time is what we call T1. So that means if you start with a random set of spins, just a glass of water, the room temperature outside of the magnet has no magnetization, and then we stick it into a magnetic field, you will see that the energy level drops down to the equilibrium value with this characteristic time. And since the magnetization starts at 0 and then goes up, this is the opposite curve. And again, the time constant of this process is the R1, the relaxation rate, or the inverse of that is the T1 relaxation time. So without knowing anything about your spin system, you can already derive that the T1 is an exponential decay. And the meaning of the T1 itself is basically the time it takes to go from 0 to, of course, 1 over E distance compared to the final equilibrium value. So I'll talk a little bit why this is interesting in MRI in general. So the T1 describes the speed in which the longitudinal mg magnetization reaches equilibrium. In MR in general, of course, you cannot measure the mg directly. It needs to be excited with an RF pulse. It brings the magnetization into the transverse plane. So once you do that, thing to notice that rotational frequency, so the spins start to rotate around the magnetic field, and the frequency of this rotation is proportional again to the strength of the magnetic field itself. And so you excite the spins, they start to spin around, and this rotating spin is actually what we can detect in the MRI coils. So the second step in this process is that different spins may experience slightly different amplitudes of the magnetic field. It can be due to just the local susceptibility or influence of neighboring molecules. So that means that the frequency of the rotation for different spins is slightly different. So it means some spins rotate fast, other spins rotate slower. So in a co-rotating frame where the average of the spins is stationary, you will see that the spins in the transverse plane start to disperse. So the factor sum of all this magnetization decays over time. Now this decay is called the T2 relaxation. So that characterizes the signal decay after you excite something. So as I said before, the spin dispersion can be caused by two different things. It can be local differences in magnetic field due to the susceptibility. So that's the magnetization of neighboring parts of the sample that changes the local magnetic field a little bit. It can also be due to the local spin-spin interaction. Basically two neighboring spins, again because it's a little magnet, the spins of the neighboring magnet influences the field the local spins experience, and that means that you get again a dispersion of this magnetization factor. Important part compared to the T1 relaxation is that the T2 is a lot faster, since there's also no energy transfer involved. It's just slowing down and speeding up of spins. And the T1, as I said before, needs a mechanism of energy transfer, because the energy state of the spin changes and it needs to couple to the thermal motion of the bus. So in general, in an MR experiment, you start with spins in equilibrium, apply an RF pulse that brings the spins to the transverse plane. They disperse, so they randomly spread out in the transverse plane with the T2 relaxation rate. And finally, on the time scale of the T1, the magnetization is restored, and you can do this all again. And let's see, so why is this relevant for just about any MR experiment you can do? It's because all the MR experiments typically involve a lot of repetitions, a lot of repeated RF pulses. So if you start with, say, a 90-degree pulse that completely tips the Z magnetization into the transverse plane, meaning that the start right after the pulse, the Z magnetization is 0. And then you wait for a while, and during this waiting time, the Z magnetization recovers with the characteristic time again of the T1 relaxation. So depending how long you wait, the amplitude of this magnetization will be different depending on the time and the T1 relaxation of the spins in question. And so if you try to go faster to speed up your experiment, well, that is fine, but then the Z magnetization here has a lower value, and then you end up with a lower signal in the end. So you partly can combat it by not using a 90-degree pulse, but say using a shorter pulse that doesn't really tip the entire Z magnetization away, but only part of it. So the advantage there is, of course, that you keep more of the Z magnetization available, so at the time of the next pulse the Z magnetization is further recovered. But of course the downside of it is that your signal is equivalently lower. So that's kind of shown here. If you do a 90-degree experiment, right, so you excite and the signal decays. If you do a semi-experiment with a lower flip angle, more of the Z magnetization is available. But of course the transverse magnetization, since you tip it only 45 degrees, is now equivalently shorter. So in a typical experiment you can calculate what this effect of these both relaxation and the excitation is. And so you have a typical relaxation time. You give an RF pulse with a certain flip angle. During this waiting time the magnetization recovers. So it's quite easy to calculate then what the equilibrium magnetization is, since you know the relation between the magnetization before the pulse and right after. And also you know this T1 relaxation that describes the relation between the magnetization here and at the end of the repetition. So you can solve this equation and figure out what the equilibrium is between the excitation that drives down the magnetization and the relaxation rate that recovers it. So if you plot the signal as function of flip angle for different ratios of the relaxation rate compared to the repetition time, and this is what you get. And so if this ratio is short, you end up what is called with a lot of saturation. If the TR is long compared to the T1, you have more time to recover the magnetization and always a higher signal. You can also see for every chosen ratio of the repetition rate and the T1 relaxation, a different flip angle gives you the optimal signal. Now there's more to T1 than just saturation and recovery of excitation. You can, instead of giving a 90-degree pulse that excites the magnetization into the transverse plane, you give a longer RF pulse that totally flips the magnetization. If you do that, you can look in an inversion recovery experiment. So in this case you start with the magnetization inverted, and of course the same process happens as what we talked before. The T1 relaxation will slowly bring this magnetization back to equilibrium. And so at the T1 time again is the time that this difference between the original magnetization and the equilibrium decays 1 over E. Frequently what is relevant in inversion recovery times is also the time that the magnetization crosses at 0, and that is roughly at about 70% of the T1 time. And this is frequently used to suppress one particular spin species, like in a flare sequence. If you time it such that, for example, the free water crosses 0 here, well, other spins that relax faster already have a higher magnetization. You can selectively image one of your spin species in your sample. General T1 measurements can be classified in 2 general categories: one saturation, one inversion recovery, as we kind of already alluded to in the slides before. So one way to measure the T1 is do an experiment or 2 sets of experiments where you repeatedly apply the RF pulses and you look at the equilibrium level, and then repeat the experiment with say a higher flip angle. Right, so as shown before, the signal depends on the flip angle and the influence on T1. So depending on the saturation level, the saturation level changes for the 2 flip angles. Say if you do a 90-degree, you get more saturation. And then comparing the average signal you get with the low flip angle and the high flip angle, and checking back into the graph that tells you the signal level is in response to the flip angle and this ratio of the repetition rate in the T1. You can derive the T1 of the sample by comparing the two flip angles here and the 2 signal levels that you measure. Another way to go around it is to make use of this inversion pulse. Right, so where you not saturate the spins, but you invert the spins, and then you measure the signal that you get out of there by at different delay times after this inversion. And you compare that also to the signal you get, say, without inversion as a reference. So this is more or less what the MMG magnetization looks like. Right, for the reference, you start at 0, it recovers. For a very short recovery time, the spins are almost totally inverted. For a very long inversion time, the magnetization is further back to equilibrium. So if you compare the signal in blue for these different inversion times, you're effectively sampling this inversion recovery curve. And it gives you another measure of the T1. Kind of a hybrid way that is frequently used. It's called an MPRAGE sequence. In this case you give an inversion pulse, but then instead of giving a 90-degree pulse at different times, you sample the magnetization with small flip angles repeatedly and make one fast image out of all the signal you collect here. So it's more a T1 weighted sequence than a quantifiable T1 sequence. Since now again the saturation or the signal level that you measure here depends on how fast the spins recover after this inversion pulse. Right, so if the spins of a shorter T1 relaxation recover farther, and the signal that you measure here will be higher. So illustrated here for the blue spins of a short T1, so you have a higher signal. Green spins of a long T1, they're more saturated. So from the signal level, again, you can derive some kind of a T1 measurement, or at least a T1 contrast. General trouble with this is that the signal depends not only on the T1, but it also depends on the saturation levels. With the RF flip angle, it also depends, of course, on the T2 star, and it depends on the system sensitivity, like the coil sensitivity or whatnot. So it's harder to quantify this. But to some extent it can be solved if you use an MP2 rate sequence, where you can make this image at two different inversion times. And then the coil sensitivity and T2 sensitivity is partly compensated. There's a few examples of measurements. This will be a multi-slice measurement for a T1 recovery experiment. And so here's the reference signal without inversion preparation, and if you do an inversion pulse and you measure very shortly after the pulse, most of the spins are inverted, so indicated by the dark color. The scale is basically runs from -1 to +1. And if you wait longer after the inversion pulse, the spins, say in the white matter, are recovered, so it gives you a positive signal, where, for example, the spins in the CSF, since they have a much longer T1, are still dark. So that illustrates how an inversion recovery experiment can be used for a T1 measurement. It shows an MPRAGE and an MP2 rate. So that is frequently used, not so much for T1 measurements, but for a nice anatomical contrast. And you can see if you do the MPRAGE itself, you're missing, for example, a large part of the lower side of the brain, because the coil sensitivity is lower. If you use an MP2 rate, where you compare two different inversion times and divide one with the other, some of those coil sensitivities are compensated. As you can see here, you recover part of the cerebellum. So you can do this high resolution at 7T and make very nice anatomical images. It's based on the T1 differences between white matter and gray matter, and of course the CSF. Another application for T1 measurements in general is also the use of contrast agents. So this is an example of an MS patient, where you give a contrast agent that can cross the blood-brain barrier if there is an active inflammation in the MS lesion. Now, the contrast agent helps to make that T1 transition faster. So the water that is in close contact with the gadolinium gets a shorter T1 term. And if you do the MPRAGE as a T1 measurement, these lesions light up pretty. Now, pure water has very little energy transfer between the state of the magnetization and the thermal vibrations, since there's not that many vibrations that have the right frequency to make this energy transfer possible. So that means pure water has a very long T1 time and a slow relaxation rate. So in the brain, to have a faster T1, you need interaction with other molecules, typically with lipids and proteins, so larger molecules that are semi-solid, and more of the vibrations of those molecules couple with the magnetic energy transition. So those have a faster T1 time, faster T1 relaxation, shorter T1 times. And then the interaction between water and the lipids and proteins is actually what governs most of the T1 relaxation in the brain. And this is through a process called magnetization transfer. This is the second part of this talk. To go into that, we have to go back to T2 for a minute. In general, if you consider the interaction of water molecules, say you have a water molecule here and surrounded by other water molecules, the question is, in a sense, why is the T1 of the water not very short? Because all the water molecules are little magnets, right? And the magnetic field of one molecule influences the relaxation of the next one. So naively you might suppose this magnetic interaction should disperse all the spins very quickly, yet it doesn't happen. Or why does it not happen is because all the water molecules are evenly surrounded by neighboring molecules, and also they're moving around quite quickly on a time scale of an MR experiment. So that means all these dipole fields from the surrounding water molecules average out to zero. And effectively, they don't see their neighbors. And therefore the T1 of water in the fluids, or other fluids in general, can be quite long. However, if you look at the lipid molecule that has a long carbon backbone with a number of protons attached to it, that is a semi-solid molecule. So in this case, the dipolar field of the neighbors does not average out, right? Because they stay in the same position, and also they don't have neighbors on the other side. So these dipolar interactions stay intact. That means this kind of molecules have a very, very short T2 in the order of just tens of microseconds. And that means, in general, we don't really see the signal from the protons in lipids and proteins because it's so short. However, this hidden magnetization still interacts with the water. And so, because the magnetization is not isolated, it exchanges with the magnetization in the water. And that is a very important contrast mechanism in the brain. So where do we find these molecules? In the brain, this is mostly concentrated in the myelin layers and other layers of cell membranes. And so this is very rich and it's basically a bilayer of lipids and proteins. And so in white matter you have 15 to 20% of the protons in these kind of lipids. And all these lipids have a long carbon chain with other protons attached to them. So in a very stylized model, you have this carbon chains, protons here, and there's N groups that also have some amides or hydroxyl molecules that are close to the water. Now, because of this dipolar coupling, the magnetization is interacting between all these lipid protons very quickly. That means that the magnetization from this molecule can effectively exchange with its neighbors, and through either chemical or magnetic interactions can actually exchange with the water. So that means effectively we have one, and this spin coupling is very fast, in the order of probably microseconds again. The spin interaction is somewhat slower, tens of milliseconds. So that means we have effectively one bars of magnetization on the lipids and one bars of magnetization in the water. So that you can just model like this. There's two pools of magnetization, but there is also some interaction between them. In general, we see only the signal from the water. However, this magnetization in this pool is relevant for a lot of experiments. So we show here. So suppose you start with an equilibrium magnetization where both pools are completely relaxed, and for some trick you can say saturate the macromolecular pool. So what can happen then is that because those spins interact with each other, that saturation also starts to influence the magnetization level in the water. Right, so you have two pools that both magnetize, you saturate one, some of that saturated spins transfer to the water, and that diminishes the magnetization of the water pool. So the combination of that is, even though you cannot see the spins directly in an MR experiment, if there is some effective saturation of this pool, it influences the water pool and therefore influences the signals that you can see. So we spent a little bit of time going through some math. If you ever read some articles on magnetization transfer, you need to be aware of some slightly different approaches to calculate this. So to characterize this system, you need relaxation rate, and we're talking about only the Z magnetization, longitudinal magnetization in this case. So you need T1 relaxation rate for both pools. You need the relative size of the pool, typically noted by F for the macromolecular pool, and therefore 1 minus F for the water pool. And then you need some kind of an exchange rate that describes how quickly the spins can transfer from one side to another. And frequently that is noted as two separate exchange rates that suggest the spins, or the rate from spins moving from left to right is different for the spins moving from right to left, and that is actually kind of misleading, since it's always an exchange, so the same number of spins goes left to right as right to left, and the volume of both pools cannot change. As you will see after we derive the equations, this makes slightly more sense. So we can derive the equations for this system by starting at the block equation, and the differences that you may find in literature stem from just different ways of normalizing the magnetization or the exchange rates. So if you start with the block equation for the longitudinal magnetization, that's basically what we wrote already, we can normalize that to the individual pool size, which means the equilibrium magnetization is by definition 1. And we can add a second equation for the macromolecular pool. For convenience, we can now scale both of these equations with the relative pool sizes. And then we can add exchange terms. So where K in this case is normalized to the total number of spins. So this is one form of the equations. One alternative form can be derived if you divide both equations by the individual pool sizes. So mathematically this doesn't change anything, of course. But now we can rewrite this exchange constant as a constant related to the pool size. So now you have two constants, two exchange rates. One related to the water pool size, one related to the macromolecular pool size. And then you get this set of equations. There's two different exchange rates. As an alternative form, there's a different normalization possible, where instead of normalizing every pool to 1 on its own. You now normalize the total magnetization to 1. That means the water pool magnetization gets replaced by 1 over F times the first formulation, and the same for the macromolecular pool, and then we can do the substitution again. And without going to the details of the mass, we'll just go to the result here, which is the bottom side of the equations. So in this formulation, again, you have two different exchange rates. The important part to notice here that now here we have the kWp for both incoming and outgoing spins. In this formulation you have two different exchange constants. So all of these systems describe exactly the same thing, the difference is just in the normalization. And if you read the literature, you just need to be aware of this and figure out which system the particular author is using. Otherwise it's royally confusing what's going on. So coming back to this picture, these two constants, so they don't really mean the number of spins going out of this pool or coming back into this pool. These constants just relate the exchange rate or the total exchange flow to this pool size. So 1k is divided by the macromolecular pool size, the other k is just related to the water pool size. Now once we have these equations, we can solve the exchange system. And one substitution we frequently like to make is writing this as terms of saturation, which is basically just 1 minus the magnetization. Again, it's just a simple mathematical trick. So in equilibrium, the saturation is 0. If you saturate the spins where the mg is 0, then the saturation is 1. If you invert the spins, saturation is just 2. So instead of going from -1 to +1, the saturation just goes from 2 to 0. That simplifies the equation, and because now you don't have the equilibrium magnetization in the equation anymore, that means you can write the system of equations as a matrix, right, and the two saturation levels as a vector. So this becomes a differential matrix equation, and that makes it easy to solve, since this system of equations can be solved by just looking at the eigenvalues of this relaxation matrix. And the solution then turns out to be a sum of two exponential decay rates, where the two rates are the two eigenvalues of the exchange and relaxation process. So it sounds like a lot of math, but there is actually a sort of an intuitive explanation for this. If you look at the signal of say a system where we have 0 saturation for water in red, but complete saturation for the macromolecular pool, right? So the spins of the water are up, the spins for the macromolecular pool are close to 0. And then as long as the exchange rate is fast compared to the T1 process, what is happening is the exchange will make the two spins population roughly equal, so that leads to a quick change in the magnetization. So that corresponds to the fast exchange term in the solution. So lambda 1, if this is the fast term, corresponds mostly to the exchange process. And then once the two magnetization levels are roughly equal, then the saturation level further in time just decays with a combined T1 relaxation rate, and that roughly corresponds to the second exponential in the solution. So if you look at the saturation over time, the saturation of the water changes quickly because the magnetization transfer out of the macromolecular pool, and then it decays again slowly to equilibrium with the T1. Now, similar to T1 measurements, the T magnetization transfer effect has also two different approaches of measuring, which are quite parallel to T1 measurements. One is again looking at the saturation level for two different conditions. So if you do an MT saturation experiment, you can have some kind of an MT pulse that, say, saturates all the lipids in the sample, and then do this repeatedly, and maybe do this for two different levels of saturation, or one case with saturation, one case without saturation, and look at the difference at the resulting saturation levels in the water. So this is one way of measuring MT. Let's skip this part. The other way is more analogous to inversion recovery experiment. Again, having a reference, and with an inversion we inverted the water. Now for an MT experiment we just saturate the micromolecular pool, and now we can do this at different time delays and effectively study this saturation recovery curve. So if you go back to this curve, effectively you start here with an MT pulse with a short delay time, and if you increase the delay time you're taking different samples on the saturation curve, similar to taking different samples in an inversion recovery curve. See, so one way to saturate or there's two ways to saturate macromolecular spins. So we go back a little bit to this slide. Classic way is to just take one pulse at an offset frequency far away from the water. Right, so the idea is that you saturate macromolecular spins that have a short T2 and therefore a very broad spectrum. So if you take a long pulse with an off resonance frequency, so it doesn't have any energy on resonance, it does not saturate the water, but because the spectrum of the macromolecular spins is so broad, right, that there's a very short T2, this narrow band excitation can still saturate all the lipids, and if you irradiate it long enough, gives you a complete saturation. So this is what is classically used in the saturation equilibrium MT experiment. Another way that we use in our lab is using on-resonance pulses. And that is just a series of hard pulses that tip the magnetization back and forth. So, quickly go to that. So what happens for very long T2 spins? So water is that spins just flip back and forth, and in the end they restore to where they came from. So spins with a very long T2 are not affected by this pulse. Spins with a shorter T2, however, they get excited and they relax before the next pulse can tip them back. So effectively that leads to a high level of saturation of the lipid spins. For the sake of time we'll speed through this a little bit. So very similar to an inversion recovery experiment, if you do an MT recovery experiment, so we give an MT pulse, saturate the lipid pool, we wait for different delay times and then see how it affects the water signal. For the very short delay time, there is not enough time yet for this saturation to transfer into the water, so you don't see much. Then if you wait for a while, the saturation level increases. So more of the saturation of the water, of the lipids, transfers into the water. And then finally, if you wait longer, the saturation level starts to go down again because of the T1 relaxation. So now finally, a little word about the combination of inversion and MT experiments, because it turns out actually inversion or T1 relaxation and magnetization transfer are very closely related. So typically in most inversion or T1 measurements, these exchange effects are all completely ignored. But however, this is not quite correct, since you can invert the water spins. You can, because of the, again, the short T2, you just saturate the lipid spins, and then during the inversion recovery, this exchange again starts playing a role, and it changes the magnetization level of the inverted water. So that means just very similar to the MT experiment. The level of saturation of the macromolecular pool influences how fast the water magnetization recovers. So this is important because in an inversion recovery experiment you have a strong RF pulse, and then the level or the time of this RF pulse changes how much saturation you infer on the lipids. So that changes the effective T1 relaxation of the spin system. So we can demonstrate that effect if you do an inversion recovery, use different energy levels for the inversion pulse, and then plot the resulting signal level on a log scale. And then you can see for a high level of saturation that is still fairly flat. If you take care not to saturate the lipid spins, so we end up with inverted water, but the lipid spins are intact, so you have a big difference in magnetization between the two poles, and the exchange effects between the two poles influences the inversion recovery curve, and effectively also making the T1 inversion recovery by exponential decay, very similar to the solution that we showed for the magnetization transfer experiment. We can show this difference if you calculate the effective T1 relaxation for two different delay times. So if you look basically at the slope, say between these 2 points versus the slope of the signal change between these 2 points. Right, so if you look with in the beginning, the T1 relaxation is faster because of these exchange effects. And then if you go to a pulse with lower RF power, you have less saturation. The difference between the magnetization in the two pools is bigger, and the effect of this B exponential decay gets stronger. And again, there is essentially the same set of equations that govern the MT exchange also governs the T1 relaxation. So the take-home message there is that basically all T1 measurements in the brain are actually bi-exponential. And to measure this properly, you always have to fit a bi-exponential decay. Now, one more note on this relaxation mechanism. These two pools, I should say, both have a T1 relaxation. And it turns out, without going into details, that the relaxation in the water pool in the brain is typically pretty slow, in the order of T1 time of 2.5 to 3 seconds. And the T1 time in the lipid pool is much faster. It can be 250 milliseconds at 3T and about 500 milliseconds 7T. So if you look at the signal, even the slow decaying signal, it is still dominated by the T1 relaxation in the lipid pool and then exchange from the water between the lipid and the water pool. So if you measure the T1 of the whole system, while ignoring the lipid pool, effectively we're seeing mostly the T1 relaxation in the lipids. And that also means that if you make a map of the slow decay rate, this is basically effectively a T1 decay map. you mostly see the white matter light up, and it closely corresponds to the measured fraction of macromolecular molecules in the voxels, effectively, of course, showing again the white matter, because you have more lipids in white matter than in gray matter. So, summary for that part: pure water has a very long T1. Main source of T1 relaxation is macromolecules like lipid proteins and some contribution from iron and other things. It is T1 relaxation in the brain is dominated by exchange between water and these molecular protons. The consequence of that is also that magnetization transfer and T1 are essentially the same mechanism and measure the same thing. They're both sensitive to lipids in the brain. And finally, of course, to do this properly, T1 relaxation is always a B exponential decay. In reality, things are slightly even more complex. There's not just two pools, but there's multiple pools. Since you have not just water and lipids, but you have axonal water, you have extracellular water, there's water in between the myelin layers. So to model this slightly more appropriately, you would have a water pool, say you have water between the myelin layers, and there's macromolecular protons, right? That is the lipids in the myelin layers that can exchange magnetization with all of those, and then the water has to exchange, crossing all the myelin layers into the free space. So a complete model of T1 relaxation and magnetization transfer would be a whole lot more complex than a two-pole system. But that is a little too complex to show. Yeah.